And hello again. In this little video here, we'll concentrate on actually using some of these double angle formulas to calculate some values. In a previous video, we established how we got to these double angle formulas using our angle addition formulas and replacing the two angles with one of the same. So sine of 2 theta is the same thing as sine of theta plus theta. And so that's how we got all of three of these double angle formulas. All right, well, let's give an example similar to one that you'll see in your textbooks. Something like this. You're given some information about an angle and asked to perform a couple of tasks. In this case, the information you're given is that the sine of theta is negative 2/3 and that theta is in quadrant 4. Your job then is to figure out, that is, calculate or evaluate the sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So the first thing that you should do in all problems like this is to construct a little right triangle so that you can think about these different ratios, sine, cosine, and tangent. And let's draw it so that it's kind of sitting in quadrant 4, like this one right here. Now let's put in the numbers. It says that the sine of theta is equal to negative 2/3. Well, if we consider theta to be right there, the sine of that angle then is the opposite over the hypotenuse, so I'll put a 2 there and a 3 there. Then, by simply using the Pythagorean theorem, I can quickly calculate what the length of the third side is. So I've got 3 squared minus 2 squared is equal to the third side squared, and so that's equal to 9 minus 4, which is equal to 5. So my third side then is the square root of 5. Now, having established what all three sides of this little representative right triangle are, I can now calculate very easily what these three main trig values that I'm going to use are. We've already been given that the sine of theta is equal to negative 2/3, so we already knew that. The cosine of theta is going to be the adjacent side over the hypotenuse, so that's square root of 5 over 3. And the tangent is the opposite over adjacent, so we can quickly figure out that the tangent of theta is negative 2 over the square root of 5. Just keep in mind here the quadrant that the angle is in is what you really need to focus on to determine whether or not these values are positive or negative. In quadrant 4, cosine is positive and tangent is negative. And another thing I'm going to point out is that even though this is negative 2 over the square root of 5, I'm not really going to worry about that too much. That is, I'm just going to leave the value the way it is without rationalizing the denominator. So our first task was to find the sine of 2 times theta, which, if you recall from our double angle formula, is 2 sine theta cosine theta. And this is how easy this is. Going back here and looking at these numbers, all I have to do is use the sine of theta and the cosine of theta and plug those numbers into the formula. It's that simple. So the sine of 2 theta is then 2 times negative 2/3 times square root of 5 over 3, and all I have to do is just simplify that out. 2 times that is going to get, I end up with negative 4 root 5 over 3. That's all there is to it, folks. It's just plugging numbers into these formulas. And in the same way, my second task to find the cosine of 2 theta, which is equal to the cosine squared theta minus sine squared theta. All I'm doing is plugging those numbers in. So I've got root 5 over 3 squared minus negative 2/3 squared, and I just have to work that out. It's not too bad. So root 5 over 3 squared is 5 over 9, and then subtract 2/3 squared. Even though it's negative, it'll be positive, but I am subtracting, so it's 5 over 9 minus 4 over 9, which is equal to 1/9. So that's it. That's the cosine of 2 theta is just equal to 1 over 9. So let's go on and do the third task there, which is to evaluate or calculate the tangent of 2 theta. And here's our formula, a double angle formula there. And just to remind you that the tangent of theta in our problem is equal to negative 2 divided by the square root of 5. So let's plug that number into the formula. That's all it takes. So it's 2 times negative 2 over root 5 divided by 1 minus negative 2 over root 5 squared. This will take a little bit more work to work through, but it's really just about calculating the numbers here. So on top, you can see that we've got negative 4 over the square root of 5. That's our top, that's our numerator of the big fraction. The bottom is going to be 1 minus, what's 2 over root 5 squared? Well, squaring that, it gives us a 2, it gives us a 4 on top and a 5 on the bottom. 1 minus 4/5. So that's just 1 minus 4/5 is just 1/5. So just taking a look at that for a second, that 4 over square root 5 divided by 1 minus 4/5 turns quickly into just divided by 1/5 on the bottom, which then I can work this out by multiplying by the reciprocal, right? Negative 4 over root 5 times 5 over 1, and just working that out gives me this, negative 20 over the square root of 5. Which, when I take that negative 20 over square root of 5 and rationalize the denominator now, by multiplying by root 5 over root 5, I get 20 root 5 over 5, which simplifies down, don't forget the negative sign, which simplifies down to simply negative 4 root 5. So tangent of 2 theta is equal to negative 4 root 5. So to sum up our results here, when we calculate the value of sine of 2 theta, we get negative 4 root 5 over 3. When we calculate cosine of 2 theta, we get positive 1/9. And when we calculate the tangent of 2 theta, we get negative 4 root 5. And that's it. That's the whole job there of using those double angle formulas. It's just a matter of plugging numbers into the formulas and calculating the result. You could stop here if you wanted to, but I would like to make one more comment about the signs of these values. This could be an important thing for you to think about, and if you've got a few extra seconds, just hang on here and look at this. We said that the sine of 2 theta is negative. The cosine of 2 theta is positive, and that the tangent of 2 theta is negative. Let's take a look at an angle that's in quadrant 4. Remember, our angle theta here for this problem was in angle 4. Let's take a look at an angle that's in quadrant 4 and see what happens when we double it. Okay? And just to make the math easier, I've chosen 300 degrees, but it would be true for any angle here in quadrant 4. If you double 300 degrees, you end up with 600 degrees, right? Well, where is 600 degrees? Well, if you plot it out on the unit circle, if you went around, starting with 0, went around, okay, you go around once, that's 360 degrees. You keep going until you get to 600, which would be right about there, at about 240 degrees. That's the co-terminal angle there for 600 is 240 degrees. That is in quadrant 3. All right, well, let's take a look at our results here to make sure that they match up. So you wind up with an angle over here. 600 degrees is equivalent to 240, and in this quadrant 3 here, the cosine is negative, the sine is negative, and the tangent is positive. However, if you pick an angle to begin with, let's say that's closer to our values here, well, let's see. If I picked an angle, let's say 330 degrees, okay? Well, that's not a very good drawing, but picked an angle that's closer to the horizontal axis there, and doubled that, 2 times that gives you 660 degrees, and if you went around the circle 660 degrees, you'd start off, you'd go around 360, then you have to go around another 300, which puts you to right there. So doubling 330 puts you into quadrant 4. And so in quadrant 4, our cosine is positive, our sine is negative, and our tangent is negative. And that's exactly what we've got here. Sine is negative, tangent is negative, but cosine is positive. So all that tells us really is that our original angle way back here at the beginning of this problem, the sine is negative 2/3 and the theta is in quadrant 4. We had an angle that is in the, let's call it the upper half of quadrant 4. Okay, so that all lines up with our positive and negative values there. That's the only point I wanted to make. See you next time.